Hello, everybody. Okay, can you guys hear me and see the screen?
Good
Yeah.
evening, Professor.
Yeah.
Hello.
Great, thank you. We still got some people floating in, but what we're going to do tonight is continue our lecture that was talking about finding deflections through the double integration method for beams. Before we get right back into it, though, does anybody have any questions they would like to ask of me?
Professor,
Yes.
for last week, I missed last Thursday's lecture, but when I was looking at the video, when we derived the equation for the deflection, I think it was the first example that we did.
Okay, the one with the point load?
Yes, the one with the point load. When we derived that, the final equation we got, you said was valid for the entire span, but we derived that using only the moment equation for the first half of the beam. So wouldn't you need to derive a second one for the second half because it would be two different cuts before and after the point load?
Normally you would. Normally you would. But in this instance, because the point load was placed exactly at midspan, we took advantage of symmetry. And that's what, and that was kind of that was the first problem we did. I didn't want to, like just completely blow everybody's doors off on the very first problem. But yeah, the first problem was doable with only one cut simply because of symmetry.
Okay. All right, thank you.
I don't think it's going to be in the double integration method, but I think I do it in the energy method, which is actually tonight's lecture. After we finish this one, we're going to roll into lecture 26, which is energy methods. And I'm not sure we're going to get to it tonight, but there's an example in there where it's not symmetric. And we have to do exactly what you're just indicating. We have to do an integral from here to here, and then add it to an integral from there to there, and then combine the results to get the final answer.
All right, thank you.
Okay, any other questions before we get rolling? Okay, so again, we are on the lecture about finding deflections of flexural beams using the double integral method. We had already done an example with a point load. Was symmetrically placed in the center, and we did an example for a uniform load where we found the deflection is equal to minus 5 WL to the fourth over 384 EI. That was the last one we did. So now we're going to start example number 3, where we're going to look at a cantilevered beam with a uniform load on it. Again, keeping it very generic, the length of the beam is L, and the load applied is a W in kips per lineal foot. So we do a free body diagram, and we have to find our reactions in order to find the equations for the moment. So the reactions that we have for a fixed cantilever beam is a vertical reaction and a moment reaction at the end. So to find the reactions, I'm going to sum my moments about A. I have the resultant of my uniform load is W times L, and the moment arm is L over 2. So therefore, my reaction moment is minus WL squared over 2. The vertical reaction is going to be equal to the W times L. So my reaction at A is WL, and it is upward. Now we need to decide on cut points. Notice though that I've taken my free body diagram and I redrew it with my reactions as I know them. WL is up and WL squared over 2 is in the counterclockwise direction. And the loading is back to a uniform load, not the resultant. How many cuts do we need?
Just one.
Just one. That's correct. Oh, I just noticed the chat here. I did assume that fx is equal to 0. Yeah. But good catch. I didn't look at that. But for deflections due to bending, any axial load on there doesn't really play into the double integral theory. It doesn't cause, it causes an elongation or shortening, but it doesn't cause more deflection. So that's also why I neglected the horizontal forces. So we need one cut point. And so we do a free body diagram of our cut point. We put on our reactions as we know them. We put on the load as applied, positive shear, positive moment, and we sum our forces. We get V is equal to minus WX plus WL. And the moment, we have, let's see, what did we do here? We're summing our moments about the red dot. So we have WL reaction times X, and that's clockwise, so that's positive, minus W times X over 2 is the load, and that is counterclockwise, so that's negative, minus my end moment reaction is WL squared over 2, counterclockwise, so that's negative, minus M all equal to 0. So therefore, M is equal to minus WX squared over 2 plus WLX minus WL squared over 2. Okay, and that is valid from X is greater than 0, X less than L. So over the whole span, we have this just one expression of moments in terms of X. Okay, so then back to our theory, dv dx ei is equal to the integral of the function moment as a function of X. And so I take the integral of this whole expression here, minus WX squared over 2 plus WLX minus WL squared over 2. And that gives me minus WX to the third over 6 plus WLX squared over 2 minus WL squared X over 2 plus C1, constant of integration. Then to go from dv dx to v, I integrate again. So I integrate the whole first result here, and that gives me minus wx to the fourth over 24 plus WLX cubed over 6 minus WL squared x squared over 4 plus C1x plus C2. It's getting a little messy, but is everybody following along? Is what I'm doing clear? Anybody have any questions? Okay. So now we need to solve the constant of integration with our boundary conditions. Okay, so this is a fixed cantilever. Keep that in mind. So if C1 is associated with dv dx is the slope of the beam. So where on the span do we know something about the slope of the beam?
It's 0 at the fixed support.
Exactly right. The fixed support on the left-hand side fixes the beam. So the deflection is 0, the slope is 0. So that means at x equal to 0, dv dx has to equal 0. So that's basically what I just said. dv dx equals 0 at x is equal to 0 because the slope of the beam is always going to be 0 at a fixed condition.
So the slope is the moment, right?
I'm sorry?
Is the slope is the moment?
No. Slope is not the moment. Here, let me draw you a quick diagram. Remember how we started last time? We started by talking about, before we go into all this crazy calculus, we talked about just drawing the deflected shape so you can see what's going on.
It's the tangent line to the moment.
That's right. So the deflected shape, it's very hard to do with a mouse, but the deflected shape is something like that. And dv dx is the slope. So at the very end of the beam, the slope is there. And that's a negative slope. It's a negative departure from the horizontal. And if I took a point over here, okay, that's the slope at that point, say like right there, it's less of a slope. So the farther out on the cantilever, the more slope you have. But the important thing to know is that at the fixed support, the slope is equal to exactly 0. Okay, so this angle with horizontal, that angle in radians is dv dx. That is the slope. Does that help?
Yeah, it's very obvious. Thank you.
Okay. All right, so we set this equation equal to 0 at x equals 0. So everywhere you see an x, you plug in a 0 and you solve for C1, and you get C1 is equal to 0. Okay, what else do we know? The second equation is relating C1, C2, and V. V is the deflection. Where on this span do we know something about what the deflection is?
At the support, there's no deflection.
That is correct. So again, the drawing I just had, at x equal to 0, we know V is equal to 0 because it's a fixed support. So then what we say is V equals 0 at x equals 0. And so, and what I did here was, this is the second equation. We know C1 is equal to 0, so I dropped that out. So I have VEI is equal to all of this plus C2. So now I can plug in for V is equal to 0 at x equal to 0 and solve for C2. And what we have is C2 is also equal to 0. Therefore, our final form of the equation, VEI is equal to minus WX to the 4th over 24, WLX cubed over 6, minus WL squared X squared over 4. And so I just bring EI around, and this is the final form of the general equation. So you can plug in any value of X between 0 and L, and plug in the values for E, I, W, and L, and you will have the deflection. So this is the general solution. But we also know that from the diagram I just drew, we know that the maximum deflection will be at the far end from the fixed support. The furthest out the cantilevers clearly is going to have the most deflection. So if I plug X is equal to L into this equation, here, here, and here, then this is going to simplify greatly. Everything is going to be WL to the 4th over something. I just combine all my fractions. And what I end up with is the maximum deflection is minus WL to the 4th over 8 EI. So that's how that one simplifies. Any questions on example 3? Oh, and here's the deflected shape again. So what we're measuring, V, is the deflection of the beam from the fixed support to the furthest end. All right, example number 4. This one's a little trickier. Now we have a cantilever beam, but instead of a uniform load, we have an end moment, an applied moment at the end. So we kind of go through this in the same way, create a free body diagram to solve for our reactions. We sum our moments about A, and we find that my reaction at A is equal to the negative of the applied moment, m naught. And my vertical reaction is equal to 0. There's no vertical forces on here, so the vertical reaction has to be equal to 0. Decide on a cut point. We only need one cut point for this particular beam there. So we create a free body diagram. There's no vertical reaction. We have positive shear, positive moment, and our applied reaction, which is equal to m sub naught. Sum our forces, shear is equal to 0. Sum our moments, and what we find is that our moment here is equal to minus the applied moment, minus m naught. And this is valid between x is equal to 0 and L. So everywhere along that span, the moment is the same. It's a constant, minus m naught. Okay, so then we follow our equation, dv dx ei is the integral of the moment as a function of x. So we plug in our moment as a function of x, which happens to be a constant in this case. And when you integrate it, you get minus m naught x plus c1. Then we do the next integral to go from dv dx to vei. So I integrate my result again, and I get minus m naught x squared over 2 plus c1x plus c2. Solve for the constants of integration with our boundary conditions. Okay, everybody should know the answer to this one now, because this is exactly the same as we just did. Where on the span do we know something about the slope?
At 0, x is equals to 0, the dv over dx is 0.
That is correct. At x equal to 0, the slope is equal to 0. dv dx is equal to 0 at x equal to 0. So I take my equation here for the slope, and I plug in 0 for the slope, and I plug in 0 for x, and I find that c1 is equal to 0. Okay, and then so then I drop down to VEI, and I rewrite it with my value of C1, which is 0. So VEI is equal to minus m naught x squared over 2 plus C2. Now, where on the span do we know something about the deflection?
At x equals 0, v equals 0.
That is right. So we plug that in. V equals 0 at x equals 0. And I get 0 is equal to 0 plus C2. Therefore, C2 is also equal to 0. And so this cleans up nicely. And we end up with V, the deflection, is equal to 1 over EI minus m naught x squared over 2. This is the general equation, valid anywhere on the span. And again, you notice that if I plug in x equal to 0, my deflection is equal to 0. Now, where on the span would you expect maximum deflection?
At the end.
At the end. X would be equal to L at the end. So the maximum deflection will be the far end from the fixed support at X equal to L. So I plug in X equal to L, I plug in L for X, and that doesn't really change much at all. So my maximum deflection is occurring at, or is, 1 over EI minus m naught L squared over 2. And I just kind of combined it there. And then this is again, the deformed shape illustration of what that moment is doing to the beam. It's bending it like so. Okay, so that's the end of lecture 25. Any questions about double integration method?
I have a question, Professor.
Sure.
So in real world, don't you need to account for the weight of the beam?
Sure.
because like for example, in this example number 4, you said that
Uh-huh.
Fy is equals to 0,
Yes,
but in reality, the weight of the beam also has the force going down, right?
yes, it does. So how would you solve that? How would you attack that?
So you need to find the centroid of the the beam, and then whatever the weight is, so the force will be on that point,
There are
something like that.
there are actually, and that's a great question. Thank you for asking that question. There's two ways to do it. And the one way to do it is to put the uniform load right on the beam along with this end moment. You have both of them on the beam. And then you just solve for your reactions with both loads. And once you have your reactions, you make a cut point and you solve for your internal moment as a function of W, the uniform load, and as a function of M naught. You'll have both terms in that summation of the moments. And then once you have that, you go through these examples exactly the same way that I did. It's just going to be a little more complicated because you're going to have a string of functions associated with W and the other function associated with M naught. But you can still solve it in terms of both. That's
Okay.
one way
Okay,
to
makes
do it.
sense.
And then there's absolutely nothing wrong with doing it that way. It's just when you get to this step right here, you're going to find, actually, I'm sorry, let's get to this step. When you get to this step, what you're going to find is that M has a function of M naught and W will both be in there. And so that's fine. You just solve it. It just has more terms. The other way to do it, there's a different way to do this. Let's see here. Okay, so example 3 is a uniform load on a beam. This could be the self weight, this could be added weight, anything you want it to be. But example number 3 solves the whole thing for just W. Example number 4 solves the whole thing for just the end moment. Because of superposition, you can then just skip straight to the end and take the answer for example number 3 and add it to the answer for example number 4. That's superposition. So
Okay.
if it's going to be too massively complex to solve for everything in the same byte, then break it up into bite-sized pieces. Do example 3 for the self weight, get your answer. Do example 4 for the end moment, get that answer, and then just add them together.
Okay. That makes sense.
Yeah, that
Mhm.
was a good question.
Thank you.
Any other questions on this double angle, double integral method? Okay, so what we'll do, so tonight is lecture 26. And tonight we're going to talk about energy methods. And more specifically, this is the energy method technique to finding deflections. Deflections for beams, deflections for actually loaded rod, deflections for trusses. So this is just another tool in the toolbox, but it also helps to understand some of the concepts of stress and strain and energy that we had covered earlier. Okay, so here we go.
Which chapter,
I'm sorry.
which chapter is that?
I knew somebody was going to ask me that. Hold on just a second. stands to reason. If I knew somebody was going to ask that, I probably should have had my book out. Okay, looks like we are now in chapter 14 for energy methods. Yep, chapter 14 starts with the guy standing on the diving board. Okay, so getting started, energy methods. A force does work when the force undergoes a displacement dx that is in the same direction as the force. So remember we talked earlier about if I climb a mountain, doesn't matter if I take the short road or the long road. Actually, it doesn't even matter if I walk, run, or ride a bicycle. The energy expended is just the force that is opposite the direction of the movement. And so the mountain I'm climbing up. So really the only thing that matters is the vertical elevation change and my weight. The energy that I expend to get to the top of a mountain is only dependent on how much I weigh, that's the force, and what the vertical elevation difference was, that's the displacement in the direction of the force, right? So it doesn't matter if I go around the mountain 50 times or if I just go straight up a cliff, it's the same energy. Units of work are actually the same units as torque and moment, but because it is a force times a direction or distance, then you have kip inches or pound inches or Newton meters. Okay, so the differential of external work is equal to the integral from 0 to the displacement of a force times the dx, where delta is equal to the total displacement. Okay, so to demonstrate work produced by a force, F1, from a hanging rod that displaces by delta 1, okay, so here's an illustration. The energy is equal to the integral from 0 to delta, this displacement times the force over dx. So if I plot this, if I apply 0 force, then I get 0 deflection. If I increase the force to F sub 1, then as that force is increasing, this rod is displacing. So as I increase the force, the rod displaces or your deflection increases until I reach like a stable F1 is, I don't know, say 10 pounds, whatever it is. That force, once you stop loading it, the load is on there and it stays at a stable deflection of delta 1. What these actual numbers are is not important at this moment. It's just that delta 1 is associated to the force of F1. Since the energy is equal to the integral of F dx, the total energy is equal to the area under the F dx curve. Okay, so if I apply the force F1 and that rod displaced by delta 1, then the energy, it's actually called strain energy. When you take a rod and you stretch it, there's energy in that rod. And if you let go of the rod, it will bounce back to its original shape like a spring. So just like everybody knows that you can store energy in a spring, you can store energy, it's called strain energy, in a rod. So the total energy that was expended or stored in the rod is equal to the area under the force displacement diagram. Okay, so the energy in this case, you can see that this is a triangle. So the external energy is half of the external force times the deflection caused by that force. Or another way to visualize this the energy is equal to the average force times the total deflection. When you start applying a force to a rod, it's not immediately the final force. You are actually applying the force. And so the more force that is applied, the more deflection that you get. Halfway is the average force. So you can think of it as the area under the triangle, which is half because the triangle is half the square, or you can think of it as the average force times the total deformation. The average force is half of the final force. Everybody okay so far? Yeah, Mustafa. For the time being, yes, we are assuming that everything is acting in the elastic range of the material. Yeah, absolutely, yes. Strain energy still applies in the plastic region, in the nonlinear. Actually, there's a whole field of engineering based on that. A lot of seismic engineering is based on the energy dissipation, I can't say that word, the energy absorbing factor of a building as it stretches and strains and cracks and yields is very important to seismic engineering, but not to this class. In this class, we're gonna keep things as simple as we can. And so, yes, that's a great question. We are assuming this entire conversation that we are only acting in the elastic region of the material. So there is no plastic or nonlinear material strains going on.
Thank you.
Okay, so now what happens if we applied F1 and we got a deflection of delta 1, but then we add another weight to the rod so that we're now up to F2 and we get a new deflection delta 2. Actually, I'm sorry, let me say it differently. We added a weight equal to F1 to the rod. Then we took another weight equal to F2 and added it again. So now the total weight on the rod, or the total force on the rod, is F1 plus F2. That's what I was trying to say. So when you put the force F1 to the rod, you got a deformation of delta 1. If you add more force, then you'll get more deflection, clearly. So F2 is the added force, delta 2 is the added deformation. So it's going to cause the rod to deflect an additional delta 2 amount. So the total deformation is going to be delta 1 plus delta 2. Okay, so the total energy now is going to be equal to the area under the curve. So the total energy is going to be equal to half of F1 delta 1. That's this section, half because it's a triangle. It's going to be equal to the whole of F1 delta 2, because that's a square. So the height is F1, the width is delta 2, and then you have a triangle up here, which is half F2 delta 2. And you can see that area of this triangle, the height is F2, the width is delta 2. So this is the total energy stored in the system that is deflecting under F1 and F2. So now we're going to introduce the concept of a virtual load. If we consider the following, if we assume that F1 is a real force applied to the structure, delta 1 is the deflection that is due to that real force. So we put a real weight on it and it deflected delta 1. This is all the real movement of the structure. But we can say that F2, that second force that I applied to the rod, F2 is a virtual force. Virtual force meaning that we're just going to put it on paper for the math, but it's not a real force. It's not something that's really being applied to the building. And because it's just to help with the math, then we can make it 1 kip or 1 Newton or 1 anything. We make it 1 so that it's really easy mathematically to account for. And then delta 2 is the deflection due to the 1 kip imaginary force that we're putting to our structure. And this might be a bit confusing at this point, but it's gonna make sense here in a minute, hopefully. So again, here's my force deflection. But now think of this in terms of F2 is an imaginary 1 kip force. Delta 2 is the deflection due to the imaginary 1 kip force. And F1 and delta 1 are real force, real deflection. So the energy, internal energy, we're going to say is equal to F1 times delta 2. That's this square here. But this square is equal to this square. They have the same area. So that is to say that the real force times an imaginary deflection is equal to the virtual force times the real deflection. The real force times the virtual deflection is equal to the virtual force times the real deflection. Yeah, this is all trickery. This is all sleight of hand stuff, but it's going to get us to what we really want is delta 1. We're going to know what F1 is because that's the problem statement. What we really want is delta 1. What we're using is kind of a trickery of energy conservation to get to another way to get to delta 1. And there it is. Delta 1, if I go back to here, delta 1 is equal to the internal energy divided by F2. The real deflection is equal to the internal energy divided by the virtual force, but because the virtual force is 1 kip, then that's going to make that, oops, let me go back here. Then it's going to make this equation a lot simpler because we're dividing by a unit load. Okay, but what we need to know is what is that internal energy? That's what we need to get to now. Okay, so we're going to go back to our basics. We got our elemental cube that is of size dx, dy, dz high, and it is under a normal stress sigma z. So our equation is that the differential of the external energy is the integral from 0 to delta f dx. From what we just talked about a moment ago, actually, I'm sorry, we do the, yes, what we just learned about from a moment ago is that the external energy is equal to the average force times the deformation. So this came from the triangles that I just explained. But the force is equal to a stress times area. So the stress is sigma z acting over an area of dx, dy. And the deformation is equal to the strain epsilon z times dz. So in other words, I put a stress on this cube and it's going to stretch that cube out. We know the stress because it is sigma z. And we know the force is equal to sigma z times an area. And we know the stretching effect from Hooke's law is epsilon z times the original length is dz. So now I can substitute all of this back into my energy equation. So instead of half times the force, I have half times sigma z dx dy. And instead of times the deformation, I have epsilon z dz. I can combine dx dy dz into d volume, just a differential volume, and sigma z and epsilon z. So then I can integrate to get to my energy, and I integrate over the volume using Hooke's law that sigma is equal to epsilon times Young's modulus E. I can plug that into here. and that gets rid of epsilon. So now I've got the integral of sigma squared 2e dv. This is your internal strain energy. Oh, let me go back. Yeah, this is write this one down. This is an equation that we're going to be working from for the other specific applications of this. But the general form, internal strain energy is equal to the integral of sigma squared over 2e times the differential volume. Okay, so now we're going to go to more specific applications, starting with the simplest is an axial load. So here's my equation I just derived. I just substituted sigma x for sigma because it's a stress in the x direction. And so sigma x is equal to p over a. So I substitute p squared over a squared. The volume is equal to a times dx. A is the surface area of the cylinder. X is the length. Then we have the internal strain energy is the integral from 0 to L, that's over the length of the member, p squared over 2ae dx. And if a is constant, then this simplifies to p squared L over 2ae. If a is not constant, then of course you need a function of a as a function of x, and then you actually need to integrate it. Like we did when doing deformations of axially loaded members, same concept. But there's our final result, is the internal energy is equal to p squared L over 2ae. Okay, so any questions about this? Energy of an axially loaded member. Okay. So what about bending moments? A little bit more complicated. We go back to our original formulation, the integral of v sigma z squared over 2e dv, start at the basic. And then remembering for bending moments, our flexural formula. The stress is equal to the negative of the moment, y over I. And we're taking moments about the ix axis, so I put ix in there. So I substitute the flexural formula squared, back into sigma z. That gives me this. And then dv, I substituted dA dz for dv. So ix equals, remember this is the second moment, so that's the integral of a y squared dA. Then I can substitute this in for here, and IA equals, oops, actually, no, I didn't. I did, yes, I did. I substituted y, uh-oh, what did I do? I did y, oh, that wasn't very clear. I had my over I squared, m squared, I squared, y squared dA. Oh, okay, I haven't done anything yet. All right, sorry guys. So I basically just squared this out, pulled the y out, and then separated my integral from the integral of v to the integral over the length, and here's the integral of the area. So this separated into two integrals, and then dv I had already separated into dA dz. So I basically, without doing anything yet, I just isolated the integral over a y squared dA here from just collecting terms. And then that becomes ix, and the ix cancels one of the ix that was squared here to leave us with the internal strain energy is the integral from 0 to L m squared over 2EIX dz. That's the general form. And then we say conservation of energy. External has to equal the internal work. Oh, okay. So this is the general form here. Yeah, this is the form we're going to work with. Now, how do we actually make this useful? How do we get deflections out of this equation? So here's where that internal 1 kip virtual work comes into. If I apply a 1 kip load at a point of deflection, then delta 1 is equal to my internal work over my pseudo force F2, where delta 1 is equal to real deflection, F2 is my virtual load of 1 kip. And so my internal work here equals this expression. So I substitute this expression in here. F2 disappears because that's a 1 kip pseudo load. And instead of m squared, what I've got is a little m and a big M. Everybody tracking so far?
What does the little m mean?
Okay, that's where we're going to get to. Okay, so the virtual load is applied before the real load, so the half factor is eliminated. That's why if you noticed, I went from half over here, the half is gone. And I went back and researched this, and basically the best I could get out of this is now expressing the square area under the curve. Now, to your question, little m is a moment due to a virtual load. Capital M is a moment due to the real load. So little m, moment to the virtual 1 kip as a function of x. Capital M is a moment due to a real load as a function of x. All right, who wants an example?
Professor, can you go back a little bit?
Yes.
How come you went from dz and then it will become dx?
Because, and this is a bit confusing. This was dz because the x-axis had to be orientated this way for the flexural formula. Remember in the flexural formula, x is to the left, and then you do the right-hand rule to find a positive or negative moment. So the moment about x shows that the x-axis has to go to the left. And that is right here, I sub x, my. So if this is the x-axis, and this is the y-axis, as we learned in our combined loading section, then the only axis left is z. So that's why I called the longitudinal axis z. Why did I do the big flip-floppy? Because once we got past all the integrals and everything, when we got down here, what we learned in chapter 6 on finding the moments as a function of x, we didn't learn how to find the moments as a function of z, we did it as a function of x. And so I made a conscious decision to switch to a new coordinate system from dz to dx so that the example problems will look a lot like and build off of what we did in chapter 6.
So does that mean that since the deflection is in dx, the actual figure uh will move from left to right?
No, 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 no. The deflection is going to be in the y-axis.
So from top to bottom?
The deflection is going to be in the y-axis. The beam is going to bend up or down,
Yeah.
right? See, the moments are in this direction. This direction of moment will cause a deflection going up and down. If we had a moment going about the y-axis, then the beam would bend in or out. But we're only looking at moments about the x-axis, our traditional positive negative moment causing the deflection in the y direction. And the z is really so that we can integrate from one end of the beam to the other end of the beam to collect all the energy stored in that beam from one end to the other.
Okay, that makes sense.
Okay, and I know that this part's a little confusing, but I had this z so that the x made sense when looking at the stress. But then I switched to x being in this direction so that when you do this problem, the x is measured from the end like you're used to in chapter 6. Okay,
So it's just the
yes,
unit that has changed.
the units?
I mean the instead of using dz, you switch it to dx.
Yeah, yeah,
Okay.
but you'll see. Um, I hate to do that. I like to be able to answer the question, but it's just a sign convention. It's just a naming convention. You'll see that all of that was up until this slide was really theory to substantiate the method. But now once we go through the method, once you see how it is applied, it'll make a lot more sense in terms of actually the application.
Okay, thank you.
Anybody else though? I don't want to leave anybody in a cloud of dust here. Is there anybody out there? Anybody else have any questions? Okay, so let's find the deflection at midspan of a simply supported beam, 30 feet long, with 3 kips per lineal foot of load on it. Now we know from the double integration method, we could just take these two numbers and plug them into the minus 5 WL to the 4th over 384 EI equation. Once I give you I and E. So we could use the double integration method to get the deflection. But using the method of work energy, we can get to the same result. Okay, so what we need to do is find the equations for the moment we need to do this for the virtual load, and we need to do it again for the real load. So little m is a function of the moment as a function of x due to a virtual load, and capital M is the same thing, but only due to the real load. So start with the virtual load. What we do, this is how the method works. You take the virtual load and you apply it where and in the direction that you would like to know your deflection. So if I want to know the deflection at midspan, I put a 1 kip virtual load at midspan. And if I think it's going to go down, then I put my virtual load going down. If I wanted to find the deflection anywhere else on the beam, then I would just apply this 1 kip load someplace else on the beam to find the deflection at that point. That's how this procedure works. So I want to know at midspan, so I put a 1 kip load going down at midspan, and I find my reactions. And by summing moments and forces, I can find that my reaction due to the one kip is a half a kip up at A, half a kip up at B. I decide on cut points. I'm going to need 2 of them, right? So I redraw the problem. Here's my reactions. Here's my applied load. And I need 1, 2 cut points to fully describe this beam. So for cut number 1, it's the same procedure we've been doing all along. I put a free body diagram, positive shear, positive moment. There is no load for cut 1, but I have my end reaction of a half a kip. And I solve for my moments, and my moment is 0.5x, and this is valid between 0 and 15 feet. So from the end to the midspan. Then I do it again for cut number 2. And I solve for this, and this one is equal to minus 0.5x plus 15 kip feet. And this is valid from 15 to 30. Now, what is really important here is that you do not, absolutely do not take the tempting shortcut and try to flip X around and measure X from the right-hand side for the second cut and from the left-hand side for the first cut. Absolutely will not work. X has to remain constant for all the pieces of this big puzzle. Okay, so here's my function for the moment in terms of X on the first half, my moment as a function of X for the second half.
Wait,
Now
sorry.
let's, yes,
Sorry, can you go back just a little bit? real
sure,
quick?
there.
So Professor, that one kip can be applied anywhere, like, but because of the problem statement, it says midspan that's wide in the center.
Absolutely, yes. Yes, if, just for instance, if the problem statement had said, find the deflection at the quarter point, then you would have put the one kip load going down at 7.5 feet from the end of the beam. Okay, so the next step, we have the equations for the virtual load. Now we need the equation for the real load. And so my real load is 3 kips per lineal foot. I'm going to find my reactions. I create a resultant, sum my moments and forces to get 45 kip reaction at A, a 45 kip reaction at B. And we decide on cut points. Because it's uniform, I only need 1 cut point. So then I sum my forces or draw my free body diagram, put my 45 kip reaction, my 3 kips per lineal foot uniform load, my positive shear, positive moment, and I solve for my moments. I have the shear here, but really what I just need is the moment. So we've done this like 100 times now, but 45 kips times X minus 3 kips per foot times X in length times X over 2 moment arm minus M equals 0. M is equal to minus 1.5 X squared plus 45X. And this answer is actually valid from 0 to 30 feet. So now I go back to my equation. My deformation delta is equal to the integral from 0 to L, little m, capital M, EI over dx. But we have a problem here, don't we? We have 2 functions for little m. How do we resolve that?
The small m is for the virtual and the capital M is for the real.
Yes, but I have 2 little m's. Let me go back here.
Do you just add them together?
Sorta. I have 1 little m, 2 little m.
You have to take from 0 to L, so 0 to 30.
So 1 little m is valid to 15 feet. The other little m is valid from 15 feet to 30 feet. So I think you guys are on the right track. What I need to do, oh, well, I got some definitions here. Moment to the virtual 1 kip as a function of x, little m equals 0.5 from 0 to 15, and minus 0.5x plus 15 from 15 to 30. Capital M is the moment due to the real load, and that is equal to minus 1.5x squared plus 45x over the whole range. So what I need to do is I need to integrate from 0 to 15 using this little m, and from 15 to 30 using the other little m, because these are only valid over these ranges. So what I've done is little m is 0.5x here and minus 0.5x plus 15 here. Capital M is minus 1.5x squared plus 45x. That goes here and here. And I have over EI dx and over EI dx. So I got two integrals. One is expressed for the first half, the other one expresses the second half. Okay, so now I can evaluate my integrals. I took the EI, that's a constant, and I put it out front here. And I just multiplied these two, oh gosh, what was that called again?
Polynomials.
FOIL method.
Yeah, that's what I did. The FOIL, first, outer, inner, last. Oh, I forgot what the term was, but the product of the two.
Distribution.
Yeah, okay. Anyway, yeah, I just did FOIL. If you guys remember that from math, whenever that was. But first, outside, inside, last. And you get this expression. So I just multiplied the two together, collected the terms so that this is as simple as you can get it, and then integrate the two. When you do the integration, right, you get x to the fourth plus x cubed and x to the fourth plus x cubed. Remember, there is no constant of integration with this method because we are, again, I forgot the mathematical term, but we are integrating over a definite term. We know where we're going from 0 to 15, 15 to 30. So there's no constant necessary in here. And so then you just evaluate this one from 0 to 15 and this one from 15 to 30, which gives you this very lovely string of numbers, which is this term at 0 plus this term at 0 minus this term, this term at 15 plus this term at 15 minus this term at 0 minus this term at 0, this term at 30 plus this term at 30 plus this term at 30, minus 15, 15, 15. That's all these numbers here. And you consolidate, it's 31,640.6 kip foot to the third. And then equation yields kip squared, but dividing by a virtual load cancels out 1 kip, which, see how this is kip feet to the third? This equation here would give you kip squared feet to the third, but don't forget we're dividing out by a 1 kip virtual load. So this becomes kip foot cubed. And then I divide by IE and all the units drop out. But be very careful about your units because this is feet to the third. And this is inches squared and this is inches to the fourth. So this is a real easy way to get your answer off by a factor of 1728, 12 to the third. And the final answer is 0.698 inches. The answer is positive. So what does that tell you about the answer?
Does it mean it's in the direction of where you put your virtual load?
That is exactly right. It means that it is in the direction that I assumed my virtual load. I assumed the virtual load was going down So this is actually a downward deflection. But this is one of those where plus or minus doesn't mean up or down. Plus or minus means that it was either in or it was opposite to the direction that you assumed when you set up the problem. Fair question, Peter. A very fair question. I've used this. I'm trying to remember where I've used this. The simple answer is that you would not use this to find the deflection of something that you could look up in a table. That absolutely fair question. And the answer is you would never go through all of this work to get this answer. I'm trying to remember though. I mean, I use this in the real world in a real application. I can't remember what the deal was, but there was something. That's what happens when you do this after a while. You forget why you started doing things. There was something about the original problem in the real world that I was trying to solve that precluded the use of the tables. It precluded the use of the double integral, but this method was still valid. This was the only method that was still valid. And I can't recall if it was because it was in the plastic region, but then Hooke's laws would not be valid in the plastic region. I don't remember. I don't want to take up too much time having a senior moment here, but I have used this in the real world on a real problem involving a steel beam or a steel pin or something. And this sucker actually solved it when no other method would solve it. It was either this method or using an empirical method, empirical meaning that you just use brute power to solve it out, like a nonlinear finite element type of problem. And I think that's what I did. I did a finite element nonlinear problem, and I confirmed it with this calculus and got the same answer. I just remember what it was I did. Okay. Did that answer your question, Peter?
Yes, it did.
Okay, great.
Thank you.
Okay, and like I just said, positive number means the deflection is in the direction of the virtual load, which was 1 kip down, so the deflection is down. Okay. Yes.
If we go back to the FB, the free body diagram of the virtual load, why did we do 2 cuts when it is symmetrical?
Here. This one, we could not use like the double integral method. This one, we couldn't do that. We couldn't take advantage of the symmetry. So this one required using the 2 cuts. And if you had not used the 2 cuts, then I'm pretty sure, though I'll be honest, I didn't try it, but I'm pretty sure that when you get to this point here, you would not get the right answer. This part of it did not yield the same answer as this part of it. I am pretty sure. There's a minus, a minus. This one is half of that one. This, yeah. So you can't take advantage of the symmetry. So we had to do a rigorous definition of the moment as a function of x over the whole span.
Okay, thank you.
Okay. Well, okay, I was trying to get caught up a little bit, but the clock on the wall is telling me that we're not going to go through this truss example in 5 minutes. And I don't want to get far enough along to absolutely confuse everybody and then not finish it. So what do you guys think? Call it a night?
Yes, please.
Next lecture.
All right, we will do that. I'm going to try to get this all in the next, we got 2 more lectures after this, right? So we'll see what we can do. We'll see what we can do. I did have a student ask me earlier today that this material that we're covering, the double integration method, the method of energy, we're going to definitely get to buckling of materials. That's a must-have for the next week. This material, is this or is this not going to be on the final exam? And that's a great question. So my answer is that the material that we have done since strain transformation, you're not going to see that material on a homework assignment. Obviously, because you're turning in your homework assignments tonight. Tonight is the due date for the very last homework for this class. So I am, yeah, here's the answer. I am not going to put on the final exam any kind of a problem statement with part A, part B, part C, solve this, solve that, go through this, go through that. You're not going to see one of those for any of this material that's been since the strain transformation because you didn't get a chance to practice it in your homework. So that means that the problem style questions are only going to be up to strain transformation, not beyond. Double integration, energy methods, buckling, and whatever else we get to next week is not going to be open to a full-fledged problem on the exam. Notice the language I'm using. That doesn't mean that I can't ask some questions about this material. But if I do, they're just going to be like a one-line question, fill in the blank type thing, just to make sure that you guys are still awake through this material. Okay?
So you're saying that it's like just the concept of this lesson?
That's right.
Okay.
Yep. I mean, this is good stuff, and I don't want to minimize it. I mean, really, all the work that we've done up till now is really to get us to this stuff that is more interesting and more advanced application. But we just don't have time to do any more homework. And so I think it's only fair that we only do homework style problems on the exam on stuff that we've actually had a chance to practice in the homework. But that's not to say that this material is not open game for the exam. It's just going to be more conceptual. It's just going to be, I can ask some questions, fill in the blank type stuff for this last couple of weeks. Okay, does that make sense to everybody?
Professor, for the finals, is it gonna be like this previous exam, that 3 questions and then you just basically add like few questions about the last topics that we had?
Well, we're almost out of time, and I'll talk more about the final next week. But the short answer is going to be that there's going to be, I believe there's 5 problems, and then there may be some questions in addition. Well, or it might be 4. I don't remember. It might be 4 with some questions, or it might be 5 with some questions. I have to go and write the thing, and then I'll get back to you on that. Next week, yes, I will have office hour on Tuesday and Thursday of next week. And we'll talk more about the format of the final when we have more time next week. Again, obviously, we're not going to have class or office hour on Thursday. So everybody, please have a great Thanksgiving. And we'll talk more next week.
Thank you, Professor. Have a good Thanksgiving.
Thank you. You too. Have a great Thanksgiving.
Thank you.
And everybody, be safe, please.